guys, I'm Juan, going to do this talk. Before we start, we didn't start yet. Before we start, I wanted to ask, so I can tailor it a bit better for your needs. How many of you guys actually like or are enthusiasts or go about like rendering? You guys, if you can raise your hand, how many like rendering? Okay, that's quite a good amount. Oh, okay. How many of you that do rendering actually are interested in Vulkan? Okay, that's a good amount. And how many actually understand Vulkan? Not so many. Okay. Okay, then I won't go into that many super low-level technical details of Vulkan because it can be. We tried this a few months ago and it didn't end very well because Vulkan is like a bit difficult. It takes a while. So we still have a bit more time, I guess. 5
minutes.
5 minutes? Okay. So that's okay. Well, nice to see so much interest in rendering. Yes. One is worried that today you see a lot of game engines, and including Godot, and that people won't be interested anymore about rendering, but nice to see that you guys actually like it. So, okay, how many here have used Godot? Oh, nice. Good to see so many Godot users. It keeps growing every year. That's nice. Nice to that you're here and not in the global game jam, at least. That's it's something. So, okay. Well, the talk will be mostly about the kind of things that we take advantage of using Vulkan. I think when Vulkan came out a few years ago, it wasn't very clear what it was for because you had OpenGL, it worked. There was DirectX 11 and DirectX 12 was still kind of like something new and nobody really quite got what it was about. When we saw Vulkan, we were like, what is this for? So we took a while actually to get the engine to be ported to Vulkan. It's still in the process. We learned a few bad things about OpenGL while porting it to OpenGL 3 and 4, more like 3.3. So we had a lot of problems with the drivers and a lot of driver bugs with OpenGL. Now, for example, we started having bugs that we didn't have before because the GPU makers just abandoned the OpenGL drivers and they started bit rotting, for example. So in the end, we really had to go to Vulkan. And when you, for example, we started getting reports from users about performance issues they had, and you would look like, for example, you render a scene with 20,000 objects, it was super slow. Because every object uses a different material, but not even a different material, a different geometry. The material was the same for the 20,000. It was really slow. So I was like, what if we try with the same geometry? Like they were 20,000, they have different geometry, but just a cube, not many vertices. We tried using the same cube and then it went super blazing fast. So there's cases in OpenGL drivers like that the driver does like validations of things under the hood and some combinations of circumstances that you don't really know, and they result in slowdowns that are kind of unpredictable. If you're like using Linux and Mesa, you can kind of see what the driver does. I'm not sure. Have any of you actually seen any Mesa code? Well, it's interesting if you want to see how a OpenGL driver works. They do a lot more under the hood than you may expect that a driver does. So with Vulkan, it's kind of like the GPU makers, they went like completely to the other side. They said, we're going to make an API that is completely low level. It does no validation for you. You can actually crash your operating system or more like your windowing system using Vulkan. Because it does no validation, you can just like do whatever you want. So they went totally the other side. I got a few lookups of my computer, especially if you run Windows, it kind of crashes on the video restarts. If you're using X11, it just dies. So you have to just restart it yourself or kill it from a terminal. So you start learning the kind of things that crash and you're like, why? They didn't validate this, it was so easy. But actually, the philosophy was we won't validate anything. Just do whatever you want. You have the full performance. We give you the gun loaded, you just do whatever you want. So it's very interesting, actually. So, well, are we on time to start, George?
Yeah, 2 minutes.
It's okay. In 2 minutes?
Yeah.
Oh, 2 more minutes. Okay, then I will tell you a bit more about Vulkan itself. Yes?
But don't you have validation layers?
Yes, you have validation layers. The validation layers are actually really useful. But the problem is that if you do something, the validation layer may spit an error. This is something that took me a while to understand, because I used to put the validation layers, and the validation layers will throw an error every time something goes out. But validation error doesn't do really anything. It just throws an error, but passes your command through anyway. So the problem is that I got a lot of crashes even with the validation layer. And I was, why isn't it validating it? But yeah, it was printing the error, but then the computer froze. So you have to put a breakpoint on the validation layer when it tells you to write an error, and then you can survive it by just like catching the error before it freezes. These kind of things are really cool when you work with Vulkan. You start learning it like just by making those mistakes, I guess. And then I was getting the actual error from the validation layer, but I didn't know it because it was freezing. So it was like, hey, no error was printed. Like, yeah, of course, it doesn't keep scrolling because it's frozen. So these kind of things it's very hardcore, but once you start getting the hang of Vulkan, I think it's beautiful that you get so much low-level access to decide how to adapt your rendering code the best as possible as your engine, to your code and your engine. Actually, one thing I found is that Godot is a general-purpose game engine. And we're okay? Okay, well, I will just conclude this phrase and start the presentation. So Godot is a general-purpose game engine. And since we need to satisfy the needs of so many games, we need to look for algorithms that are kind of all-rounders, you know? Maybe there's algorithms for, I don't know, for cooling the scene or for doing rendering, shadow mapping, different kinds of materials that are better for different kind of games. If you were making your own AAA super high-budget game, you will be fine doing your own stuff. But when you have a general-purpose game engine, you need to find all-rounders, you know, algorithms that will work for most of the games, and maybe add some tweaking options for different kind of games. But mostly it should be like good performance overall, but not best performance for specific use case. Maybe some users just take the code and optimize it for a specific use case. But yeah, it's interesting. Vulkan is really good if you want to like extract the latest, the smallest drip of performance out of the API. If you're making like a custom game made in Vulkan. But for something general purpose, it's a little more complicated. I think they didn't design it so much for it. So there was a lot of trickery that needed to be done. But yeah, it's very interesting. So if you're going to learn Vulkan, just good luck. It's very nice. So I will start with a few facts about Godot. Little information about the game engine. Godot is fully open source. We make an MIT licensed engine. It only uses compatible third-party license, so we don't mix proprietary or GPL or anything, just MIT compatible license. And we have it hosted on GitHub. One may think like, why making an open source game engine? What's the point of doing that? And many people don't know that, like, of all the software industry revenue, the whole software industry, like everything that writes code and sells it, the whole software industry revenue, out of all that revenue, 25% comes from the video game industry, you know? But when you hear about open source, you don't really hear about games. You just hear about Python, Apache, MongoDB, like things that are my productivity, business, services. So there's kind of a big gap in open source in general for whatever is games, I think. So Godot tries to fill that 25% missing for the open source software. So we feel our mission is important, even if it's kind of fun because, you know, we go to events like GDC and they're like, open source, go to an open source event. And we come to open source events, games, go to a game event. Like, so we're kind of like in the middle of something. We believe our mission is super important, but we are still in a limbo. So, well, yeah, we're fully open source. We have a really active developer community. This actually is old. We have over 1,000 now contributors, like well over 1,000. This has some months, and it's already went from 800 to 1,000. We have more core contributors. In fact, the Godot 3.2, we just released Godot 3.2 some days ago. had like almost 400 contributors. So there's a lot of people really interested in making this engine happen and contributing. It's, I think, the third or fourth most fastest growing project in GitHub or something like that. And we have like hundreds of PRs opened every month. So it's quite a growing project. We have a very active user community. Again, this is all, we just released 3.1, so this probably keeps going. So yeah, we have like a large community on Steam. We publish Godot on Steam. So we know we have a lot of, we now have like over 900 reviews in overwhelmingly positive. So yeah, if you go to Twitter, if you go to Reddit, if you go to Discord, if you go to IRC, Facebook, you will find really large Godot communities, really helpful. We try to make sure that the tone is always nice and friendly. So, well, let's go about, let's end with the facts, go with Vulkan. So, Godot used to be a proprietary game engine. Ariel, Mansour, and I had our company for a long time. At some point, we open sourced the game engine, like in 2014, and it started growing. Back then, it was mostly meant for mobile. It had 3D rendering, but it wasn't very good. It was just OpenGL 2. When Godot 3 came out, we ported to OpenGL 3.3, so we could use newer features and use OpenGL ES3. At the time, it was a few years ago, seemed like a really good idea. But the truth is that OpenGL on mobile is broken. The drivers are all broken. Mobile devices don't get updated. So it was a pain. And then, yeah, we saw that OpenGL, when Vulkan came out, they said, yeah, this is going to be an alternative. We're going to continue working on OpenGL. Lies. It's abandoned. Nobody cares anymore about OpenGL. It's dead. So one thing about OpenGL is that the API design does not really map very well to modern hardware. It's not really, when you learn Vulkan, you realize what the hardware actually does. And you understand that OpenGL doesn't really, like, I will give you a very small example since so many of you actually are interested in rendering. You know, in OpenGL, you can like set the vertex buffer, you can set the textures in use, you can set a lot of rastering operations like the winding of the triangles, or if you draw lines, or if you draw quads, or quads in Node anymore. Triangles, lines, points. You can change a lot of things, and then you call the draw function. Did you know that when you do all these things, changing the state, OpenGL actually is patching the shader. It actually is modifying the code of the shader. It has a shader in memory that you bind the shader. You change all these things, then it binds the shader. If you change like the shader, it needs to re-patch the shader with all the changes you have done. So there's a lot of code, invisible code inside of OpenGL that you don't know, that is patching the shader and doing a lot of work every time you change those states. The APIs are like Vulkan, which are called, it's not entirely stateless, but it's mostly pipeline-based. It's called pipeline-based. You just create like one object with all the states. And if you want to change the state, you just create more of those objects, you know? If you want, the pipeline has like the shader, and all the states you set in OpenGL, like the vertex buffer format and the geometry and the anti-aliasing, everything, just in one object. So the thing is, when you set a pipeline to draw, it just sets everything at once. And it's super, super fast. This is really fast. So Vulkan forces you to be, to just get your data together properly. And when you set everything together, it's just much faster. So these kind of things make it much more optimal to draw a large amount of objects. When we started porting the engine to Vulkan, the first thing we noticed was the huge increment in performance, even in the 2D engine, because we just call GL draw arrays, like every time we draw a primitive. And just using Vulkan, even if you're doing the same amount, like not the same, but similar amount of cost, the performance was like, whoa, it was impressive how much So Vulkan is more modern than OpenGL. It's more up to date. For example, if you want to use ray tracing extensions, now there's going to be, it's only NVIDIA, but soon there's going to be like an official RTX implementation for Vulkan. So this is not any longer in OpenGL because, as I said, OpenGL is dead. So all the new extensions like HDR rendering, a lot of these things are just coming out for Vulkan. OpenGL is just ignored nowadays. This sounds a bit weird, but it really works as an entry barrier because we have the problem that, for example, all the rendering, we thought that we were going to making OpenGL 3.3 compatible, which dates back to DirectX 10, like 2008, 2009, I think around that. So you can run all the high-end Godot 3 renderers and shaders in really old hardware. And truth is that that doesn't work in that hardware because the hardware has too little video memory, too little limitations, it's slow. So with Vulkan, we can just make sure that if you have old hardware, you're not going to ruin it because it's just designed for modern stuff. And we don't have users complaining, Godot is slow, because yes, you run it in 10 years old hardware and you're putting all the pretty effects on. Of course, it's going to be slow. So now it's a nice entry barrier, which means that we can focus on like optimizations and new features and everything, and people that uses Vulkan will be able to run it. And if you have a computer that does not support Vulkan, you're going to be using the OpenGL renderer, which is the compatibility render, which is designed for hardware, so you will be fine anyway. I mean, less confusion for the users is good for us. One of the new things we added to Godot is creating a new layer, which is rendering device. Now, this is very interesting. The rendering APIs, actually, even if Vulkan looks really, really complicated, because it is, you can actually abstract to a higher level API really easily and make something really simple, because now you only have like pretty much the textures, the buffers, the frame buffers, and even some APIs like Metal don't even have that. You have the shaders, the pipelines, and then the render list, and that's it. There's not so much. Actually, amazingly, even if in some aspects Vulkan is really complicated, a lot of complexity that came from the time of OpenGL has been lifted because now a lot of things are more general purpose than they used to be. So in Godot 4, we're going to have the visual server, which is the main abstraction for rendering. It's the entry barrier for anything that has to do with rendering. And we're going to have two rasterizers. One is going to use RD as rendering device, and rendering device is what abstracts Vulkan. We can make it abstract now Metal or DirectX 12, or there's some people porting it to PlayStation. We can't do it because we're open source, but they can use to port. It's much easier to port rendering device to Vulkan. And then we have a rasterizer that is GLES2, and maybe we will add some GLES3 functionality. And this just uses OpenGL ES. So we have a completely different, I mean, Visual Server abstracts the API, but then you're going to have a completely different backend depending on modern stuff or compatibility stuff. So this is transparent to user. You just switch if you want to use OpenGL or Vulkan, and everything just works. Whatever is not supported in OpenGL doesn't appear. It's just hidden. So well, the other thing that users requested a lot in Godot that you couldn't do before, that you will be able to do in Godot 4, is that you will be able to access from your scripting language or whatever you want, like C++, to rendering device, which is the Vulkan abstract, like the rendering abstraction. So if you actually want to do like more advanced custom rendering on the engine, now you will be able to, because you will be able to insert your own code during the rendering loop. That hopefully will be very nice. It was one of the most requested features. And yeah, it's eventually portable to more APIs. There's like porting, if you wanted to port Godot 3 to the PlayStation, you have to write the entire rasterizer, which is really huge. For Godot 4, you just port like rendering device and that's it. It's much, much smaller. So another thing we're going to have in Godot 4, we decided it was the best way to go is, at first, we tried to do a rendering, Vulkan rendering code that supports both mobile and desktop. But as we started working on this, we realized that mobile and desktop are really completely different architectures. It's not even worth trying to use the same code for both. So Godot is going to have a high and low-end Vulkan renderers. This is separate from the OpenGL legacy renderer. So the high-end will be just for desktop. We're just going to use, like, for example, let me give you a few examples. Like on desktop, Vulkan has something called descriptor sets, which is the amount of, like you could call it uniforms and other things that you combine to shaders in groups. Like on desktop, it's like, I think the limit is 16, but on mobile it's 4. So when you have more, you can optimize more, a lot of things. So we were being restricted to 4 just for mobile. Then at some point, it's not worth it. Let's just make the high-end use this. For example, on desktop, you can have something called indirect texture addressing. You can put all your textures in a big array, and then you use an integer to address the textures. This works fine on desktop. It has very little cost. On mobile, you just can't do it. And for example, on mobile, you still have really low texture limits. Like, I think you can, some architectures like ARM, Mali drivers, don't let you have more than 16 textures in total, or samplers. Actually, not even samplers, just textures. You can't have more than 16 textures per shader. While on desktop, this is infinite. You can have all the textures you want. Maybe the samplers are limited because it's a hardware limitation, but the texture you can have as many as you want. So the problem is that the difference between what you can do on mobile and what you can do on desktop right now is so big. It's so big. It doesn't really make sense to make something that works for both. You know, you're going to be crippling the desktop just to make mobile work. So we're going to have high and low render. I think for Vulkan makes the most sense. Also, for mobile, there's something you can do it's a Vulkan feature, which is called subpasses. Have you heard of subpasses? Well, subpasses are something you can use on mobile due to how mobile chipset works. Like mobile have a lot of when you have something when you render on desktop, it's just brute force pretty much. It just draws all the triangles to throw one after the other. On mobile, the screen is divided like in tiles, in cells, and every cell has a list of the triangles that touch this cell when you render. And then at the end, it rasters all the triangles. They do it this way so they can have like more parallelism. And actually, it's like even if you render forward, it's always deferred because it only shows the last pixel that was drawn after. It's like a mini deferred rendering a tile. So because they work like that, maybe you want to have many passes. Like for example, you do a deferred renderer, and the first pass you want to render all the materials, and the second pass you want to do the shading. So if you have sub passes, you're telling the mobile driver that after this pass, I'm going to do shading. So if a tile is done doing the rendering of the triangles, it can go to the next pass while the other tiles didn't finish. So it's so different. Mobile and desktop are really different. So you should probably, if you're going to use Vulkan, it gives you such low-level access to this kind of things that it's a waste to try to make something that works on both. Just make one that works for mobile, just make one that works for desktop. That's what we ended up doing with Godot. So the idea is that they are still both compatible, and you will be able to switch between the high and low-end renderers at any time. Well, as I was saying before, Vulkan is designed for, I explained you this before, it's just designed for low bottlenecks, like low amount of bottlenecks, just very low driver overhead. You just can, it's amazing. You just do a lot of calls, draw calls. You can have like, I don't know, 50,000 draw calls in Vulkan, and it uses so little CPU compared to OpenGL that it's amazing. So the first thing, as I was telling before, that we saw when moving from OpenGL to Vulkan was a massive improvement of performance when just drawing a large amount of objects, 2D or 3D, it's just a massive improvement. One thing that people may get confused is that, yes, Vulkan is faster, but calling the API is mostly faster. Like, if you have a very simple scene, like just one room with a few things that are furniture and really complex shaders, it's going to run the same in OpenGL and in Vulkan. Because the shader performance is the same in both. That doesn't change. But if you have a really huge scenario like a city or, I don't know, underwater or something really big that you can see really far away, yeah, Vulkan will make a big difference there. Like for really large stuff or something that has a lot of small objects, that's going to make just a huge difference. So, yeah, that's kind of the same. For 2D, it improved, the performance improved hugely. It's impressive how fast it is. For 2D, it's very difficult. Like when you work on 2D on OpenGL, you usually want to implement things like batching because there's a lot of, just put everything in an array and then send it to render because the cost of the draw call itself is kind of slow in mobile, especially in mobile. But with Vulkan, it's like, since there's no validation between the draw calls or anything, you can just throw the commands and it doesn't seem to really have any performance impact. That's really impressive, how well the drivers are optimized for a very high amount. And if you want to even optimize it better, what you can do is simply like run like the render list. You can separate it. You have imagine you want to render 20,000 objects. You can run threads that each, like you want to run 8 threads. Each one renders a chunk of the objects in a separate part of the list, and then if you put them together and so on. These kind of optimizations are great. So this is really important. It's a very big advantage of Vulkan, but it's very often overlooked, is that OpenGL is very buggy because it's very complex. If you look at an OpenGL driver, it's huge. It's really, really big. You can even, if you look in Google, you can read horror stories about people working at NVIDIA or AMD working on drivers. Like, for example, they were saying, I think at the time OpenGL 4 came out, I think I remember reading that AMD decided to rewrite their OpenGL driver. And they started, because the old one was too slow, and they first rewrote it, and it was very fast. But it was very incompatible. It didn't work with a lot of games. So they had to start adding patches to make it work better with different games. By the time they ended up adding all the patches to make it work like the old driver, it was slower than the old driver. Because, and this is AMD, I mean, this is the top company that makes these kind of things. So OpenGL is very complex. It's very difficult to optimize because you need to optimize the way you think games are going to use it, but then games may use it a different way. It's typical software design problem. If you try to make something super flexible, you're going to end with something complicated, and then it's not going to be useful because users don't really want to use it that way. They still want to use it different. So with Vulkan, they were like, we suck. We can't make this kind of complex APIs. But just let's make something really low level and let the users do whatever they want. And because of that, the APIs are so simple. They map so directly to the hardware that they are very less prone to have bugs because it's just much smaller. If you look at a Vulkan driver, like the Mesa drivers, it's just much smaller. It just maps much more directly to the hardware. They're very interesting. I think this was a really good decision. At first, when you start learning Vulkan, you're like, what? This is so complicated. Why they made it so complicated? But in the end, you realize that what you write is going to be a lot more effort. That is going to work much better, and it's going to be like less buggy when you run it on different hardware. Which isn't to say that you just, if you have NVIDIA or AMD, for example, you still need to try everywhere because there are things like barriers. For example, Vulkan has something called barriers, which you use to synchronization points between different kinds of tasks. Like, for example, compute. You do compute, and then you want to use what you did for compute for rendering and use it as a texture. You need a barrier, both for waiting until the compute is done and for converting the resulting image to something readable by what is rendering. You need this kind of barriers, which you need to put everywhere in Vulkan. And Vulkan barriers are really complex. They have a lot of options, and not all the hardware implements all the barriers. You know, I think NVIDIA implements them like more coarse, and AMD is more fine-grained. So, and Intel just like doesn't care about anything. I think it's like my experiments with Intel is whatever you do, even if you forget all the barriers, still works. So it's really weird. So Intel is just weird, but the thing is, because of this, I had problems like you get something to work, like even in the same AMD drivers, I got things to work in AMD, in Mesa, but didn't work in the official AMD driver for Linux, and then you can swap it, and then it works in one and doesn't work. Then you go to NVIDIA and just doesn't work. On Intel, it always works. It's amazing because it's just surprising. I don't think they even super barriers in Intel, but well, that's what I was saying. Less complexity is less points of failure. You still have to test in all the hardware, but less prone to bugs. One problem we have with OpenGL is that OpenGL doesn't have a standard way of catching the shaders. So our users often complain that an object appears on screen that was never rendered. And even if you pre-compile the shader before, it still has like a delay because the driver waits until everything is ready to render to just actually compile the shader. So with OpenGL, we have a lot of stalls all the time. So users have to resort to doing making like a loading screen that actually is a plane that has all the objects that need to be rendered, with all the materials, but you don't see them. They are behind a wall. So that actually forces it to actually compile all the materials before you go into the game. This is very, very typical with OpenGL. With Vulkan, what they added is something called SpearV. SpearV is like a shader bytecode. You compile GLSL. You can actually compile HLSL, which is very popular because it's the Microsoft one. People that do rendering prefer DirectX. I don't. But HLSL is very popular. I don't like it, honestly. I think GLSL is nicer, but well, anyway. You can compile to SpearV from either of the languages on Vulkan. And the interesting thing is that SpearV is not really a shader bytecode that gets executed by the GPU. It's more like a middle, if you have seen compiler theory, it's like the SSA form of the shader. It's kind of pre-optimized up to a point, but it's still not a bytecode. I mean, it's not something you can put on a virtual machine and on a GPU and run it, more like it. So the interesting thing is that it is faster to go from SpearV to the actual GPU bytecode than going from GLSL. It has also the problem with OpenGL. For example, one problem we have is that if you have to list all the GLSL compilers, you have, for example, the AMD one, the NVIDIA one, the Intel one, the web browser one because of WebGL. You have the mobile ones, like, for example, the Mali one, the Qualcomm one, the Tegra one, the Apple one, because Apple now no longer uses PowerVR. They make their own GPUs. So now we have the Apple compiler for GLSL. So there's like 10 compilers for GLSL. And one of them is always going to break because parsing text is much more difficult than, in theory it isn't, but in practice it is. Parsing text is more error-prone than parsing just a bytecode that has very specific instructions. So SpearV has the advantage that once it compiles to SpearV, you know it's going to work. And it's faster to compile from SpearV to actually the bytecode. The thing is the following. The only thing you can actually send imagine you want to distribute your game. You can distribute SpearV shaders, but you can't distribute pipeline objects. You can actually get the binary of the pipeline object because the pipeline object, you have shader code, you compile it, you get SpearV. SpearV, you combine with all the rasterizer data, like which kind of triangles, which kind of frame buffer, which vertex format, everything. All this, you get the pipeline state object. The pipeline is platform dependent. It's even driver dependent. You can't even, like, if you make a game and distribute it for AMD, they may change the driver and it's not going to work anymore. So you can use to cache it locally, the pipeline on your computer. You have to cache it even saving the driver version. There's a few articles about that. They're pretty interesting because it's very easy to break something caching a pipeline state. But the thing is that even that, compiling SpearV to pipeline state is really fast compared to just the whole thing. In fact, I don't want to go sidetrack too much, but there's WebGPU coming. You probably heard of WebGPU. There's a big discussion now. We have Apple on one side. You have Google, Microsoft, and Mozilla on the other side, because Apple wants to use something called WHLSL, which is a text format, and all the others want to use a SpearV for WebGPU. And it's been years, and they haven't agreed. Apple really doesn't want to have anything to do with Chronos. They are even deprecating OpenGL. They are like, stay away Chronos. And all the other people are, no, SpearV is amazing. Why not use SpearV? We have a lot of tooling for SpearV, which is amazing. We can convert it between a lot of different languages. So they are completely in the completely. I don't think they will ever agree. So we'll probably see WebGPU with SpearV for these browsers and with WHLSL for Safari. That's probably what's going to end up happening at this point, because Apple just doesn't want to concede anything. So I actually went into arguments with people from Apple because they really defend the stance on WHLSL. And my experience with Godot on WebGPU, on WebGL, compiling a GLSL shader, it takes a long time for web because it's so many validations for security. So just using bytecode, it's probably still dangerous, but it's faster. So that's the. Well, another interesting thing about Vulkan is threads. When you hear about threads and Vulkan, the only thing that probably comes to mind is what you heard about the secondary command buffers. You probably, if you are going to read about Vulkan, you can use secondary command buffers. You create each one in a thread, and then you put all of them together and then send it to the rendering. It's faster. Yeah, it is faster. But there's many things that are really cool that you can do with Vulkan. Like the first is that since it takes PRV and not GLSL, and even if it takes PRV and whatever you want, you can just compile shaders on threads and then you feed the PRV. It's super efficient. You can actually create multiple render lists, not just one with multiple secondary command buffers. You can create multiple render lists at the same time, which is also amazing. Like imagine you're rendering like shadow mapping. I need to render like directional light shadow mapping. You need like the 4 splits that are typical to this. You can like just create one render list for each at the same time, like as an example. You can do a lot of really amazing optimizations in Vulkan with that. The other thing that is really amazing is all the queues with asynchronous texture and buffer transfers. When you start learning Vulkan, one of the first things you see, the first is Vulkan device, and then you see the Vulkan queues. The Vulkan queues are really interesting. It's like, by definition, one of them has to be rendering, compute, and transfer, and then it has to have one transfer one and one compute one, I think. I think it was something like that. The interesting thing is that, for example, imagine you're running the game, but you want to load a texture asynchronously. What you do is you just use the transfer queue for that. You just allocate the texture because texture allocation is completely independent of whatever you are doing. So you just allocate the memory for the texture, and then you use the transfer queue to send the texture while you're still doing your normal rendering in another thread. So that's super efficient. I really like that. And you can do the same with buffers. If you want to upload geometry, textures, everything, you use the transfer queues for this. Or even if you want to do things on a thread for compute, you can run compute at the same time as. So all these kind of things are really nice. I actually really enjoy the way it works. It's super complicated, but once you understand exactly what it is, it's really enjoyable. And you can make a lot of really nice optimizations. So another interesting thing about this is when you learn, if you come from DirectX 12, like or DirectX, and you go to Vulkan, it's going to appear really complicated because Vulkan forces you a lot of things that are normally not necessary for desktop, because these things are actually more optimal on mobile. The secondary, well, I already talked to you about the render passes. You can just break the rendering render passes so the tiles in the mobile GPU can do work in parallel, even in separate passes. Otherwise, it has to finish and then go to the next one. No, this is more optimal. The image barriers are interesting. Like, for example, you can use something as a render buffer, and then you want to use it as a texture, and you want to do a lot of work like that. Since you have to specify all the conversions between what you're using the image for, you can actually make a lot of interesting optimizations. So yeah, it's interesting because it kind of sucks if you're going for only desktop, but if you want to optimize for mobile, there's a lot of opportunities there that are really interesting. So the last thing is that since we used OpenGL, we didn't have compute. There was OpenCL, but it was never well supported because NVIDIA kind of sabotaged it. There's a lot of, how you call it, like a lot of internal politics in rendering. It's amazing. So NVIDIA sabotaged OpenCL. So what they ended up doing it, and yeah, Apple proposed it and then abandoned it. It's so weird. So the interesting thing about compute is in Vulkan is that you just use it with GLSL. It may seem a bit weird because people use compute just see OpenCL or see CUDA, but GLSL is pretty nice for compute. I mean, you can still do things normally, and it's pretty like to the point, you know. And a lot of optimizations can be done. Like, for example, normally in OpenGL, if you want to do a full screen effect, you draw like a quad. Or some people even draw a triangle, so it doesn't render the middle, like the middle line, which supposedly is faster. So well, there's a lot of things, but in compute, you just run the compute directly. You don't have to go through the drawing the geometry. It just does compute, so it's super interesting. And we are actually exposing compute to the user because if you see a lot of games, it's very interesting. Compute now is so complex that you can use it for gameplay. You can, like, if you want to make a game that has like 10,000 enemies, You can totally destroy your CPU trying to do this, or you just can use compute, and compute works fantastic. And the interesting thing is that in Vulkan, you can have more than one device. Vulkan has the BK device, you can have more than one BK device. So you can just have your device for rendering, and you can have your device for doing game logic, which is really interesting, especially on desktop. But you can do really complex game logic, like internally it's going to still like send one thing at a time, supposedly. I don't really know the implementation details, but you can still do it, and it works really well. You can optimize your games a lot with compute now. I think this is not something that is used much on game development, but I see in compute a huge opportunity to optimize lots of types of gameplay. So, and this is just a few Godot related things because the talk is about Godot. One thing that we are doing in the new render in Godot is that this is a kind of usability thing. You're making an engine for people to use. So you give them an option to, in an effect, you give them an option. Do you want to look ugly or pretty? Like quality, low and high. And user will always put high because like it looks better, like why not? And then they go like, wow, this is really slow, this engine sucks. So we learned that mistake, so what we're doing now is moving everything related to the quality and performance. We move to the general settings of the engine, and we put it like, this is slow, this is fast. Hoping that this will be a bit more obvious for the user that you're like making these mistakes. And also, this is more like a way that Godot works. In Godot, when you have project settings, you can have overrides. Like for example, if it's going to run on mobile, you can override the setting for mobile. And having the quality settings on the project settings allows, for example, if you want, this is the depth of field setting, you know? Box is super fast, but looks like a box is kind of a weird depth of field effect, but it's super fast. If you use it for something small, it's okay. And circle, it's super slow, but looks amazing. It's only for like ultimate dedicated GPUs. So what you can do is you can put an override, depth of field shape. If you are targeting mobile, you can override this and go from circle to box. And you can have, for example, an override for low-end and high-end renderers. And the high-end can use circle, the low-end can use hexagon, for example. So this is pretty cool, the new things we are doing. And lastly, this is the last item. One thing that we went from OpenGL to Vulkan, but we never had DirectX rendering. So we always kept all the interpolation, the mid maps, and everything in the texture, which is what happens in OpenGL in Godot 3. But now, textures and samplers are separate, and it's really cool because if you separate them, you can have as many textures as you want, just using the samplers. But now users will have to move this, like for example, now we have this in each node for 2D. You have to configure if you want which kind of filtering you want. And if you make materials, you have to configure the filtering on the material, no longer in the texture. That's the last change we have to do. This, again, improves performance and makes sure you have unlimited textures, but the way you work on it is just a bit different. That's all. So, well, this concludes the talk. If you have any questions or want to know know more about Godot or Vulkan or anything, I'm here to answer questions. You were first, sorry.
Since you mentioned web GPU, what are your plans for it?
That's a good question. It would be interesting to make a rendering device for web GPU because it's very interesting. I don't think there is any Vulkan over web GPU. Could be easy to at least test it if we had a Vulkan wrapper for web GPU. But we're probably going to have to write a backend for it. That will hopefully be very interesting. I don't see that it's going to be this dispute between Apple and the rest of the world. Doesn't seem like it's going to get solved. So I can imagine that the SpearV tools guys are going to make something to convert SpearV back to a text shader so it runs on Apple. So yeah, that's kind of what I think about it. I guess it's going to work eventually. It's going to be a bit messy on Safari probably, but yeah, the idea is to implement it eventually. Probably for Godot 4.1, not for Godot 4, which more or less is stable now. But yeah, that's it. And you wanted to ask something?
Is there any reason for Apple to want their WM?
I have no clue. Yeah, sorry. he asked if there is any reason for Apple to deny. I really don't know what's going on. It's internal politics within the companies. For us, people outside, doesn't make any sense. I think Apple exited Kronos at some point because Apple was part of the Vulkan working group to some point, and then they exited Kronos, and they have nothing to do with Kronos anymore. Maybe that has anything to it, but what GPU is actually W3C, is not Kronos. But SPIR-V is Kronos, so maybe because they don't want to have anything with Kronos, I really don't know. It's just speculation. I don't know what. That's.
Also, does iOS support Vulkan?
Oh.
And if so, it has SPIR-V support?
No, iOS and Mac OS don't support Vulkan. They support Metal. The thing is that it's not really a secret if you dig into it, but Apple knows that nobody really cares about Metal because the gamers don't really use Mac. So what they did recently is just add more features to Metal. So the Molten BK, which is the wrapper that runs Vulkan over Metal, just works better. They secretly did it, let's say. Apple is like, it's a very secrecy company. You won't see them at any event. They don't have the public engineers. It's like so in the end, it works really well. We may eventually port rendering device to Metal if we see that there is a benefit and improvement in performance, because why not otherwise? But in the meantime, right now, it's working with Molten BK. It works really well. I run it on macOS and it just works, so it's okay. Any other question? Oh, well, let's go right to left. Sorry, you started.
Okay. When you talked in the beginning, not about rendering, but about Godot, you mentioned how the development is going and everything, but how about users? Games using your engine, how does the community look from this direction? And also, because like now we're talking about devices, Mac, iOS, everything, do you know where Godot is used more?
That's kind of complicated. Well, if it's the question is more about the community, if I understand, what they use it more and what they are expecting. The biggest complaint, the problem is Godot started as a 2D engine, mostly. It has 3D, but almost nobody used it. So nobody even bothered to use it and report bugs. When we rewrote it in OpenGL 3.3, more people started to use it, and they had a lot of complaining that it was slow, that it needed features and a lot of things. So at the same time, we realized we weren't going to continue working OpenGL because it just didn't work in a lot of levels. So we had to set the render in stone for 2 years, fix a lot of the bugs because 3.0 was a very big release. And now we are porting everything to Vulkan and trying to satisfy all the demands from users about like improved performance, more features, more modern features, more portability, working on more platforms. So right now, the direction is trying to cope with all the user demand. It's like the engine is slowly going from mostly 2D engine to a 3D engine too, but yeah, it takes a while until everything. I think the Vulkan 1 is going to be really cool. I mean, it's going to be almost on the same level as using like the high-end render in Unity or Unreal. So it's going to be more or less in that same level, I hope. Or at least it will be close enough that everything else that is missing can be added without that much effort. So yeah, that's the situation. Wait, we're going. Yeah.
So the Vulkan branch is now merged into master. Does that mean that
next week's probably, or end of this week probably? Yeah.
Does that mean that it is fully integrated? You are done with the Vulkan integration?
Oh no, not close. It's going to be broken for a while in master. I mean, it's going to. You shouldn't port your game to Vulkan yet. Some people that love living on the edge are actually publishing their game on the Vulkan branch, but you should probably not do it. Probably by the middle of the year, the Vulkan branch will be complete, like May, June, or July, and then we will focus on stabilization. So release will probably be of Godot 4 second half of the year. It will be very usable probably by the middle of the year. You already will be able to use it fine. It's just going to have bugs. Just for developing, it's okay. For releasing, maybe not so much. And when we can actually release will be a few months later. So that's kind of the roadmap. But yeah, it's going to be totally broken in a week. Yeah. Oh, sorry, you are.
Is it going to be possible to port games from 3.2 to 4?
Yeah, porting games from Godot 3.2 to 4 should be much easier than it was going from 2 to 3, which completely broke a lot of things. Most of the data remains compatible. You should be able to port your project. Maybe the scripts, the biggest change may probably be that you have to adjust the texture options in the material now because they will be gone from the texture. And the fact that GDScript is going to suffer compatibility breaking changes, we will not be so terrible and will be really good. He's doing them, not me. But it will be really much better. We actually may make a script. We can just parse the old ones and convert to new ones probably. So probably an export tool will be needed, but compared to the pain that she knows,
Yes, I had part of my
exporting your game from 2 to 3, this will be a lot less,
Hey, but it works.
painful. So yeah, that's it. We have time for more questions, or we are?
Yeah.
Okay.
So Godot 4, what is it gonna use on desktop Windows platforms that don't support Vulkan?
Do Windows desktop platform exist that don't support Vulkan?
Oh, absolutely. NVIDIA does.
Oh, you mean the older computers that have a GPU that don't run Vulkan?
Yes.
Uh,
No drivers.
No, that's going to keep using OpenGL. The thing is that those are all and have, I mean, what limits you in those platforms is not so much the feature set, but the resources and the performance. Like if you make a game with Vulkan in mind, you're thinking of the GPUs that have maybe 4 gigabytes of video memory, are really fast. The older devices that don't support Vulkan, which is kind of like the DirectX 10 level devices, they usually only have like 200 megabytes of video memory, and they are usually like just slower. They don't have usually as much. Maybe a high-end one has a bit more, but in average they are not as powerful, and they will still not be able to run the game. So if you want to make for 2D games, it's fine because they will look the same. It's just going to work. I mean, it's not going to have a lot of difference. But for 3D games, if you want to make something that uses all the highest end rendering features on those computers, it's just not going to work. I mean, it's going to work, but it's going to be slower. So you should probably use something like, instead of voxel tracing for global illumination, you may want to use like mapping, which is faster if you want to run on that device. But yeah, that's kind of the goal. So we have more time. Yes. Any other questions? Or yes.
About the rendering backends. I don't know if Godot has a PBR pipeline.
Yeah, it is PBR.
Well, if you want to implement new rendering techniques, you have to implement it for each backend, say for the low-end renderer and the high-end renderer for Vulkan.
No, that should be the same. It should work. Godot also, one thing we discussed a lot, which may be interesting for you if you are into rendering, is that Godot is meant to be an easy-to-use game engine. So one thing we are not implementing, as an example, is temporal anti-aliasing, because it means you need to let users that make shaders understand that they need to get a hold of motion vectors, and it's super difficult. I mean, it's already difficult for really big games that have a lot of budget, so expecting our users to be able to maintain motion vectors is probably not worth it. So what you're going to do is find alternate ways to do the same. Like, for example, the high-end rendering Godot is going to use forward rendering with cluster lighting, which is kind of trendy now. It's like, I think, what most new games use now. Like the new Doom, for example, uses that, and I think many new games are moving to that. So maybe then you have the problem that some things have more aliasing that are not just the geometry. So we are like using other techniques to like reduce that aliasing and still have a very stable image, as an example. The lower end rendering may use different techniques. Maybe it's just forward single pass or maybe on the older devices will be forward but multi-pass, which is better for really old stuff. But the shader you write, Godot gives you like a GLSL to write your code, but it's not the GLSL from OpenGL. It's like a managed GSL that is very easy to use, has auto-completion, has a lot of outputs already assigned for you to write. So you write that code, and then that gets compiled for the high end, for the medium end, for the low end, and you don't have to do anything. And if you want to implement like custom lighting, you can like write light shaders, and you have, for example, you have the vertex shader, the fragment shader, and the light shader, if you want the code that runs for each light. So if you want to read something custom, you do that, and then that's going to be compiled as different. The different rendering technique will still run your shader in different ways, and you just write it once and it works. Well, any more questions, or are we okay? Yes.
Are you running validation 3 now? In 4.0?
Running?
Vulkan validation. Do you have any errors?
The Vulkan validation layers? Yes. Well, to debug, it's always we always run Vulkan validation.
So, do you see errors in your work of the port?
I think there's nothing now, but who knows? I mean, I usually develop on NVIDIA and test on AMD and Intel, but right now it's not meant to be stable, so there's probably some errors if you run in different. When it's stable, it's not going to have any errors, of course, but right now, yeah, it's typical that you use something that works in one platform and then the other uses. Also, NVIDIA has their own validation layers besides the Lunar G. So usually it throws different errors. The NVIDIA ones are usually like, nah, I don't care about that. So just turn them off. But it was the same with OpenGL. They just give you too much information usually. They assume too much about what you're doing. But yeah, the idea is that you can anyway turn it on and run it. And we're going to have one of our contributors is setting up a farm that if you have like commits and PRs and everything, it's going to run benchmarks and things, and it's going to like capture if there is a regression in performance, regression in quality, if there are validation layer errors that appeared. So to avoid these kind of cases, we are trying to use CI for these kind of things. We actually got a really nice donation from AMD to the GPUs and CPUs to make this little farm. So it's going to be pretty cool once it's working. Yes?
Is there any key differences between WebGPU and Vulkan, or is it like WebGL and
WebGPU is more like Metal, because Apple proposed it. So yeah, it's so funny because, sorry, I shouldn't say that, but they proposed WebGPU with WHLSL, and everybody was like, well, let's be in good terms with Apple. Like, we could have done Vulkan for the web, but let's do WebGPU, you know, because it's okay. Metal is easier to validate than Vulkan. And they went with Apple. And they told Apple, yeah, but we'd like to use SpearV, not really. And Apple was, well, let's discuss it. Like 4 years later, Apple is like, no way, not touching SpearV. So yeah, that's what's happening.
Sorry to interject. This is not correct.
No?
Tomorrow is going to be the lecture about WebGPU. And
Really?
you can give more information.
I will be. You're going to give more information? Really?
Yes.
You're all witnesses to this. Don't forget. Okay. So yeah, I hope this is solved at some point, because it's really annoying. To be honest, WebGL sucks pretty much. It has too many problems. It's okay for simple things, but porting a game engine to WebGL has too many shortcomings. Especially shader compilation is just a big pain. So I hope if this situation is resolved at some point, that would be fantastic. I really hope this gets solved. So I will assist your presentation. Any more questions, or are we okay? Okay, thanks everybody. It's been a pleasure.